Atoms are made of protons, neutrons and electrons. Electrons are used in chemistry, but the centre of the atom, the nucleus, contains far more energy than simple chemical reactions. The nucleus contains two types of particle, the proton and the neutron. The proton has a positive charge and will repel other protons because of their similar charge. The neutron has no electromagnetic charge, but it does contain particles, quarks, which have a strong nuclear force colour. It is the colours of the quarks that make up the protons and the neutrons that cause them to attract and to repel. For the purposes of this discussion, we will simply say that protons and neutrons are attracted to each other through the strong nuclear force, which is more powerful than the electromagnetic force, which repels protons from each other. Because of these forces, a graph of the number of neutrons in a stable nucleus against the number of protons does not produce a linear graph. A stable nucleus can mean anything. A nucleus is stable if it doesn't fall apart. However, all nuclei will eventually fall apart and decay to single protons. You just need to give them enough time. For the purposes here, we can take stable to mean that a nucleus holds together long enough to be measured, or a year, whichever you feel like. We also need to remember that the elements in the periodic table are only a few of all the stable nuclei that exist. There are hundreds. All the stable nuclei will be the elements of the periodic table, plus all of those elements' isotopes. For hydrogen, the most simple element containing just one proton and one electron, we have three possible nucleus arrangements. Hydrogen is defined by its single proton on the periodic table, but one proton can have one neutron to form deuterium, or it can have two neutrons to form tritium. These are all stable as defined above. Now you add in all the other elements and their isotopes and you get a substantial catalogue of stable nuclei. Tell a lie, tritium isn't stable. It's got a very short half-life, but you can still measure it. If you plot the number of neutrons against the number of protons for each of the stable nuclei with the entire periodic table and all their isotopes, you put the neutrons on the y-axis and the protons on the x-axis, you get a curve which initially starts off as a linear straight line but will gradually curve upwards, meaning that there are more neutrons than protons in stable nuclei. As the nucleus gets bigger, it needs more and more neutrons to keep it stable. Unfortunately, this addition in neutrons causes the nucleus to become unstable in different ways. The ways in which nuclei become more stable and move around the NZ curve, as it's called, are discussed in the next podcast.